To this week's pre-seminar, which is given by Margarethe Limbach from Charles University on an introduction to the CFI construction. Take it away.
Yeah. Hello, everyone. Nice that you are here. I'm explaining today the CFI construction, which will be used later in Jos's talk. So he uses some kind of variation of the CFI construction, and we thought it would be a good idea that you have seen the original CFI construction before. So the general idea of the CFI construction is to have two structures which are not isomorphic, but which can't be found out to not be isomorphic by a specific algorithm. So in this case, this is the Weisfeiler-Lehmann algorithm, but there are now like multiple different variations of the constructions for like different kind of problems. Okay, so because this is about the Weisfeiler-Lehmann algorithm, I do a very quick introduction on what the Weisfeiler-Lehmann algorithm is and like how it works, so you can later like relate it to the construction and get kind of an idea why this algorithm wouldn't see that those things are different. I'm not going to prove this because this is actually quite complicated. Okay, so first of all, CFI, what does that mean? That's just three names. CFI is Kai Führer Immermann. Yeah, and they have like one paper which proves which gives this construction for graphs that cannot be distinguished by Weisfeiler-Lehmann algorithm. So Weisfeiler-Lehmann algorithm is a heuristic for graph isomorphism, and it has some like parameter k called the dimension. And yeah, the higher the k, the like better the algorithm is at deciding isomorphism of graphs, but also the longer the algorithm runs. So the algorithm, so this is the k, Weisfeiler-Lehmann algorithm. And this starts by giving a coloring on k tuples of the vertex set. And the first color of a tuple is the so-called atomic type.
By the way, this is my control.
Ah, that's what it does. Thanks. And so the atomic type is just a way to record when you have a tuple of vertices, whether those vertices, like two entries, are the same, or if two entries are connected by an edge or not. Like, so, oh, this is actually way nicer talk. So this is the initial coloring of the algorithm, and then this is a refinement algorithm, so it runs over multiple rounds until it realizes that it doesn't change anything anymore. So there is the color refinement step, which, so given a coloring C, in like some set of colors, the new color of a vertex is the tuple of the old color. And then, oh, like, this is not a vertex, that's a vector. And the new color, we give the old color and then some long tuple of colors. And this, it's a multiset of tuples, actually. So this would be first the atomic type of if we append some vertex to the tuple V. And then we record all the colors where we one by one replace every entry of the tuple by W. So this would be like W to VK, and then so on, and then. So this is now a tuple of K plus 1 entries, and we do this for every vertex of the graph. So this is now a very, very big color object, which is now assigned to our vertex. And the idea is that that we run this over multiple rounds until vertices which have the same color keep being the same color. So this is what refinement means. So in the beginning, some vertices have the same color, and then we run it over one round, and then it will maybe figure out that some vertices were related in a different way, so they get different colors, and we run this over multiple rounds. And at some point, like the vertices are as distinguished as they can be by their type. For example, if this graph would have an automorphism, then this coloring would never give two vertices which are mapped by an automorphism from one vertex to another, would never give different colors to those. But this is not perfect, so this doesn't distinguish isomorphism because, so it might be that two vertices have the same color even though they are not mapped by an isomorphism to each other, and this would then be because we didn't choose a high enough K. Okay, so this is the algorithm the construction was designed for. And so the next is now, what is the construction? Okay, so we start with a base graph B. And then also we have some set, and this is a subset of the integers from 1 to n. And we have some notation, and the notation says that for each vertex, EB of that vertex is the set of all edges that are incident to this vertex. So BC is for some. And now how do we generate our graph? So the graph is called G index S, and the vertex set is given as a union of a lot of sets. Namely, we first union over all vertices of the base graph. And then we also have some union over the edges of the base graph. And are those sets? So for each vertex of the base graph, we look at the subsets of the edge set, which are incident to this vertex. So we look over all S in B. But we do not include a vertex for each of those subsets, but only for those of a certain parity of cardinality, and this depends on whether the B is in the subset S or not. So either this is odd, so congruent 1, if B is an S, or 0 otherwise. This is the point where I should have at some point said that this and this here is actually the vertex set of B. That would have helped, right? Okay, so this is what XS of B is, and very important, this is a large S, and this is a very small s. Like this. Okay. And this is large S again. So this is the vertices which belong to the vertices of the base graph. Then we also have vertices which belong to the edges of the base graph. And this is, for each edge of the base graph, we have two vertices, which we call WE1 and W0. Okay, so this is all the vertex set of the constructed graph, and now we need some edge set. And most of those edges are between a vertex of the base graph and an edge of the base graph, and they basically encode whether this vertex and this edge are incident, and whether the edge also is in this corresponding subset here. So this is BS W E1 if the edge is in this subset and then we have the same with E0 if and only if the edge is around this vertex but not in the subset. And then additionally, we also always put an edge between the two, like E1 and E0, like of the same edge. Okay, so this is the construction. What does this now do? I mean, I told you a construction for one graph. The goal was to find two non-isomorphic graphs. So we have a lemma. And this lemma says that if we are fixing the base graph B and the number of vertices n, then we have that GS is isomorphic to GT. So if we're taking different sets S and T out of our vertex set, then this is isomorphic if and only if the cardinality of S is congruent to the cardinality of T, mod 2. So, and where do we find the two non-isomorphic graphs now? This is if we take like any two sets which are not congruent, mod 2. And the idea is somehow that those graphs are not isomorphic, and we can globally somehow show that they are not isomorphic by like checking for which vertices we have taken the edge set around this vertex where there are only like odd number of edges, and for like how many we have taken the edge set where there's an even number of vertices. But as long as we do not look globally at all vertices, we can't know whether the parity is odd or even. And the algorithm never globally looks at all vertices at the same time because it only ever looks at k-tuples. So the theorem, which is the one we were working towards, is if we choose our parameters right, then this gives us this pair of graphs we were looking for. So if n is k plus 2, and the base graph is the complete graph of n vertices, then the graph G index with the empty set and the graph G index with the set that has only one element, in this case called 1, are not isomorphic, but this also can't be distinguished by Weisfeld-Lehmann K. And there is one, so this, I mean, you can just show that it goes through, and then maybe I gave you a little bit of an impression why this is, but there's also one relation with a system of equations, and I thought this would also be interesting, so I show you the equations real quick. Here. So we have those sets of edges which are around a vertex, and we choose like all kinds of subsets of those. So if we have some variables and they belong to all the edges around the vertex B, so we go over this, then we would want this here to be congruent 1 if B is an S, and we would want this to be congruent 0 if B is not an S. But if we think of those like, okay, do we take the edge into the subset or not as a global thing, then we would maybe want to take the edge or not depending on what end vertex of the edge we're looking at. So those parameters here and also the vertices over there, they say vertex B, edge E on vertex B. But this edge has two end vertices, and we might make different choices. And we can see this in the graph. So if we want to choose everything consistently, we would go towards that XEB is always congruent, or in this case even equal XEC, or BC is E. But in the graph, we see like two different constructions for whether this is fulfilled or not. So either we have this this situation if both of them are in. So this is WE1, this is WE0, and those are the two end vertices of E. So if we choose both of them into those small set S, it looks like this. If we choose both not into this set, it looks equivalently just the other way around. And but if we choose them non-consistently, then it looks like this. And this can be very easily and even locally distinguished. So this is how this construction relates to a system of equations. Okay, that's all I wanted to show you today.
Right. Questions for Anna?
Yeah, so this is how you so you mean why this theorem is intuitive or what? Yeah. Yes.
Other questions from online? No, then let's thank Anna again. And we'll be back around 4 for the main seminar.